Hey everybody, we're gonna go through, I just like took that thing. We're gonna go through this graphing worksheet and explain, because I think a lot of people are wondering how to do this. And I have some of my peeps here to help me out. So, Matthew, what do we do first?
Make the graph and the scale.
Right, good. We gotta make a scale that's gonna show this data nicely, right?
Yep.
So Connor, what do you think? We have 5 seconds. What do you think we do for a scale on the bottom?
Yeah, so from 1.
From 0 here, right? So we want to make the origin 0. And then we have 5 seconds, so do you want to make 4 boxes 1 second, or maybe 5 boxes 1 second?
5 boxes.
Let's do 5 boxes equal 1 second. So if you do that, that means that, well, you know what? Our seconds are all nice and round numbers, so that's going to be easy. So we just stretch them out so that we can see more of the graph. Because if we just go 1, 2, 3, 4, 5, our whole graph is going to be right here, and it's going to be kind of squishy and hard to see, right? Yeah. Okay, so we go 1, 2, 3, 4, 5, and that's 2, and that's 3, and that's 4, and that's 5, and that's all good for seconds. Okay, now I would probably put time in seconds down here just to label that axis. And what's on the, Colton, what's on the Y?
Distance.
Good. So we have distance in meters up here. Sterling, what's my max distance?
It's going to be 22.4 meters, so you can probably do 1 per square.
If I did 1 per square, yeah, let's count up. So if I was 5, 10, 15, 20, 25 should be good, right? Okay, so let's go. We're going to make that 5, 10, 15, 20, and this is 25 up here. So we don't know the exact numbers in here, but we're going to place them. Okay, so now we're going to go and place every point on our line. And I'm going to make a big point so you can see them. So at 1 second, we're at 6.2, right? So we go 1 second, I got 5 here, and so it's somewhere in here, I guess. Somewhere like that. Does that look okay? What's my next point? 9.4? So maybe just under 10 or about there. Colton, what's my distance at 3?
13.8.
13.8, so just about 14 right there. Sterling, where am I at 4 seconds?
17.5.
17.5, so this is 19, 18, 17.5 would be there. Matthew, what's my last one?
22.4.
22.4, so this is 20, 21, 22.4, somewhere there. Okay, now, a lot of you, what you did is you took your pen and you went link, 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 link. That's not how we do this. Okay. The purpose of drawing this graph is to get a relationship between these two variables. And so we might not touch the line on any of these points, but what we want is we want to take a straight edge and we want to be as close to as many of the points as possible without, well, you might go through some of the points or you might not. In this case, I think we'll be close to a lot of them. I would go maybe somewhere around there. There's not like an exact way to do this, but you want to be something like that, okay? How's that look to you guys? Pretty good. So we're in line with a lot of these points, but we might not touch any of the points exactly, and that's okay. Because we want the relationship between these two variables. We want to be able to predict as closely as possible where the next point would be, okay? If you were going to get a relationship from here, we need the slope, right? So to find the slope, we're not going to look at our data, because we could do that without a graph. We want to find the relationship between these two variables, and so we're going to find the slope from the actual line. So we're going to pick 2 points on this line. It's kind of nice if you pick a point, say like right here, where it's in a crisscross of the graph, so you can see where it is. So that point is, the x value is 4 point, what is that, 4.8, I think? Because this is 2, 4, 6, 8 whole number. So that's 4.8, and we're at 21 seconds. That's that point, okay? And that's really, I made a new point there. And down here, maybe we pick, this looks good right about here. It's a nice crisscross. So those are just the points I'm going to use for my slope. Do you guys need to go? Feel free. You can go if you need to. Okay,
Yeah,
good.
no, I don't.
Good. So this is at exactly 5, and it's at 0.8 seconds. Okay, now how do you find the slope? What you do is you draw this out, and draw this down, and you're going to here. And this is my slope calculation. So slope is rise over run, right? And in math, they teach you that y2 minus y1 over x2 minus x1, right? But that's really just rise over run. y2 minus y1, x2 minus x1. You're really just going, you're measuring this, which is my y2 minus my y1. It's just how high you've gone in that space between those 2 points. So this, we're going from, we started at 5 and we went up to 21. So our rise is 16, right? It's from 5 up to 21 is 16, 21 minus 5. So this is going to be 16 here. And our run is, we started at 0.8 and we went to 4.8, so that's nice and simple. 4.8 minus 0.8 is 4. So this is going to be 4 seconds here. And so 16 divided by 4 is going to equal 4. And you might be thinking, well, what does this mean? Well, if my slope is 4, that means I'm going 4 meters every 1 second. So my velocity, in this case, is d over t, which is the same as my slope. My rise is the distance change, and my run is the time change. So this is 16 meters in 4 seconds, which is 4 meters per second, and that's the velocity of the object. Okay? So that's how you do that first part. The second part, I'm going to erase this all. Is that thing still running? Can we just make sure before I erase this? It's still filming?
Yeah, so for me.
Okay, good. Thank you, Connor. I'm going to erase this, and I'll post this on the classroom so everybody can have that as a reference. Go back to it. Now the second graph down below, and I'm just going to put my key on there that I did before. If you scroll down, here's my slope calculation that I had earlier. It's a little bit different. I got 4.4. So your slope might not be exactly 4. It might be 4.4 or 3.8. That's fine. That's totally fine. Don't worry. Down here, the second graph, if you did it right, it's going to look like a curve. It's not going to be straight. What that means is that whatever this object is that we graphed, you might say this is nonlinear. It's actually parabolic. It's a quadratic function. You don't need to know that right now. You just know it's not linear. It's not straight, right? And that means that the slope is changing as we go up. That tells us that the object is accelerating. Its velocity is not constant. Okay, so what do we do with that? How do we get a relationship out of this? This is something you do not have to do for your velocity lab, but you will have to do for your acceleration lab. So the way we do this is we check and we see what kind of relationship this might be. If something is accelerating, then it turns out that if we square this bottom variable, it will show us that this is a quadratic relationship. And so that's what I wanted you to do on the back. If you look at the back, you'll notice that the data is the same. This is the back of the sheet, but this is the same data as the second graph. But this time, instead of graphing the distance over the time, I get you to square the time. So 1 squared is 1, 2 squared is 4, 3 squared is 9, etc., etc. So I literally just squared all those times. And now we're going to plot d versus t squared instead of just d versus t. So notice I made a different scale because now my numbers go from 1 to 25 instead of just to 5. So you make a bigger scale, but we plot the same distance numbers on, same distance numbers, not from the first graph, but they're the same numbers as the second graph. But we plot them with the time squared instead of with the time. And what you find is that it straightens out then. And so, because this is y equals mx plus b, and we can find a slope there, I did a slope calculation on here, and I think it's around 2 or so. Let's just do it again. I need a couple points that are good points. There's not that many good points on this one. Maybe this one here. And see any other crisscrossing ones? Not really. Maybe this one is kind of, look for one. There's not a good crisscross one, so look for one that's right in the middle. How about this one? So that is, if this is 32, 34, 36, 38, 40, that's 32, 34, 36, so that would be 37. It's 37, and the x value is 15, 16, 17, 18, 19, so this is 19 on the x and 37 on the y, and this one here is, that would be 2 on the x, and what is that, 4? Yeah, 2, 4, 6, 8, 10, that's 4, 2, 4. So if we draw this slope calculation graph again, our rise is going from 4 to 37, so this is 33, and our run is going from 2 to 19, so this is 17. So our slope is 33 over 17, so pretty close to 2. I don't know what that is exactly. 16 would be 30, 17 would be 34, so we'll say close to 2. If you got 1.9 or 2.1, that's fine. And so the relationship of this line, remember our y equals mx plus b graph. In this case, b is 0, goes right through the origin there, so we don't need that part. And our y, in this case, is still displacement. Our slope is somewhere around 2. Yours might be 1.9, 2.1. And our x in this case is not t anymore, it's t squared. So this would be the relationship that you would use for that graph, and this would be the equation that we have at the end. This tells you that because it's squared, it tells you that the object is accelerating. So if you think of 1 second, 1 squared times 2 is 2, so you go 2 meters in the first second. But in the second second, 2 squared is 4, times 2 is 8. So you keep getting faster and faster, covering more and more distance every second. That's how you do that. Hopefully helpful. Is that helpful, Connor?
Yep.
Awesome. Okay. Can you hit the stop button on the phone for me there?